Good day to all of you. In this class, we shall discuss on trying to consolidate the design process and try to streamline the way in which we would design the various components of the magnetic and the electronic components of the DC-DC converter. In the last class, you recall that we did discuss briefly on the inductor, the magnetics of the inductor, reviewing the basics about it. This class, let us consolidate the design of the inductor, and then we shall look at example designs of how we would rather than example, I would say the process of the generic process of designing the DC-DC converter, taking some converter topologies as an example. So, let us consolidate the inductor design. So, step 1, obtain the value of the inductor. Obtain the value L of the inductor. And this is normally obtained using the Faraday's law or the Faraday's equation, V L is equal to N d I L by dt. And you try to obtain this knowing all other aspects of the Faraday's equation. So, this is step 1. So, let me name that as step 1. Now, step 2. Step 2, like we step 2 is to obtain the area product, as we discussed in the previous class. We would like to link the electrical and the magnetic parameters, magnetic and mechanical parameters, and that we have done through two physical parameters called the core cross section area and the window area. And the core cross section area and the window area are together combined. So, you have the core cross section area, the window area as discussed in the last class, the product of which is called the area product. And again, as we discussed in the last class, for the inductor design, this is given as 2 times the energy in joules divided by kW, Kc, J, Bm. So, here you have E, which is the energy that the inductor needs to store, and that is in joules. Kw, which is a factor for the window area called the window factor, and this has a value of around 0.6 for single winding inductors. For multiple winding inductors like the flyback transformer, see, the flyback transformer is not actually a transformer by operation, it is an inductor by operation. It is a multiple winding inductor, and for this the K factor is the order of 0.3 to 0.4. And actually it depends upon the windings, and if the number of windings are large, it can go even as low as 0.2 for a very good skilled winder. Okay. Then Kc is the crest factor. In most of the cases you can take it approximately equal to 1. J is the current density and expressed in amps per meter square. 3 into 10 to the power of 6 amp per meter square can be your starting value. And remember that this varies between 2 amp per meter square, 2 into 10 to the power of 6 amp per meter square to 5 into 10 to the power of 6 amp per meter square. This is a designer choice, and depending upon the power levels, the designer would choose a current density for the copper in between these ranges, that is 2 to 5 amp per mm square. Then Bm. Bm is the maximum operating flux. So, if you take the BH curve, a slight deviation, let me have the BH curve, the virgin spec, which is like that. So, let us say this is called BSAT and this is minus BSAT, but the operating point may be much well below BSAT. So, let us say this is Bm. So, this operating maximum flux density may depend upon the BSAT, and the BSAT depends upon the material. So, if you take for example, a ferrite material, which is the one which is normally used for DC-DC converters and any high frequency applications, the BSAT is around 0.3 Tesla, and Bm you can choose around 0.25 Tesla. And if it is the CRGO, CRGO is nothing but the acronym for cold rolled grain oriented silicon steel. And this has a flux BSAT of around 1.2 to 1.4 Tesla, and one may operate at 1.1 Tesla. CRNGO, this is cold rolled non-grain oriented silicon steel, which are normally used for motors where the flux fields are radial in nature, and this has 1 to 1.2 Tesla as the BSAT. So, around 1 Tesla. So, this is 1.1 to 1.2, and then you have few other materials like powdered iron, around 1.5 Tesla. So, people may use up to 1.3. You have the amorphous glass around 1.6 Tesla, and so on. There are so many materials, but however, most of the DC-DC converters use the ferrites and operate at frequencies the order of 20 kilohertz to 100 or 200 kilohertz, depends upon the nature of the or the characteristics of the ferrites. So, coming back, Bm is about 0.25 Tesla for the inductors. So, this may be used to obtain the area product, and from the area product you will select a core having an area product greater than this, and you will have AC selected and AW selected, which will be slightly different from what you have calculated, because you would have chosen a core with a slightly higher value of AP. Next, step 3. Step 3 is permeance, written with the with the capital Greek capital symbol. Now, the permeance, for sometimes the inductances are manufactured with the air gaps distributed throughout the core uniformly, and these have much lower relative permeability than the transformer cores, which have very high permeability and permeance, and there is no need for energy storage. However, in the case of the inductance, there is need for energy storage, and therefore, the reluctance has to be higher, and if the reluctance is higher, the permeance will be lower. So, if you are using a core where it is made specifically for inductor application, the manufacturer will give in their data sheet a factor called the AL factor. In nanohenry per turn square. This is nothing but the permeance expressed in nanohenry per turn square. If this is not available and you are using a regular transformer core, and to the regular transformer core you are applying an air gap, then you need to do some calculations. Now, let me draw an EE core like this. Now, let us say these are the two parts. Normally, the central limb will have a cross section which is twice the cross sections of the outer limbs, and the two outer limbs, therefore, the two outer limbs together will have an equivalent cross section which is same as that of the central limb. So, when the flux, rate of flux flows, it divides divides and flows through the two limbs. Now, if you provide an air gap, now let us say you insert paper of thickness Lg by 2, let us say of that thickness. The moment this is raised up, this also will raise up. So, there is a gap which comes through here, each having Lg by 2. But as the area of cross section of the outer limbs is half, they are together equivalent to 1 Lg by 2 amount of reluctance. And therefore, equivalently you could say that this core is something like this. Where this gap is Lg, equivalently Lg, that is this Lg by 2 and this Lg by 2 together add up to Lg. Now, if we have a core cross section like that, and let us say this whole length starting from here up to here in the magnetic, core, we call that Lm, then the total path is Lm plus Lg, and the reluctance is Lm by mu naught mu r AC plus the air gap portion mu naught AC, because the relative permeability for air gap is 1. So, this is the reluctance, and we can take out mu naught AC, you have Lm by mu r plus Lg. So, this is the reluctance, and what is the permeance? Permeance is nothing but 1 by reluctance, and that is given by mu naught AC by Lm by mu r plus Lg. So, understand that here, if mu r is very large, it is around 3000 for most of the ferrite materials. If this is a large value, then Lm by mu r can become very small compared to this, that is Lm by mu r becomes less compared to Lg, and therefore, the permeance of a gapped core is almost equal to nothing but AC by Lg. However, it is always recommended that you use the exact formula. This, for quick calculations, you could always approximate and then use it in this manner. However, on the other hand, if you had the AL factor as given by the manufacturer for gapped cores, for cores which have been made for inductor purposes to store energy, then from the AL factor is nothing but the permeance value. Now, what do we do with the permeance? Now, we know that the permeance is linked to the number of turns, and therefore, we come to step 4, which is calculation of the number of turns. So, the permeance is nothing but L by N square, or N is nothing but root of L by permeance. And if the L factor is given, it is root of L by AL. And this way you calculate, and in this way you calculate the number of turns. Then step 5. Now, step 5, you need to find out the gauge of the wire, the copper wire. You recall that in the last class, we discussed about a wire, the cross section of the wire, which is equal to IRMS current flowing through the wire and the permissible current density in amp per meter square. So, you have the RMS current in amps by the current density amps per meter square, how much you want to permit, and you get the wire cross section wire cross section area in meter square. Now, once you get the wire cross section area in meter square, go into the wires table and look at the wires table and pick out that wire which has slightly more cross section area than what is given here. And while you are picking out, be careful to pick the copper cross section area, because the wires are normally having two parts. One is the copper inner core with an outer sheath, which is the enamel. So, in the wire data sheet, while calculating cross section areas, you have to take the copper cross section area, or basically the radius of the copper without the thickness of the enamel, and take the pi r square of the copper portion of the conducting portion of the wire. So, that would become the wire cross section area. Then, after you have chosen the wire cross section area, and you will get a wire which you are going to use, and I will call that a wire selected, because this is what you will be using to wind. And then step 6. So, in step 6, you make the window area cross check. So, what is it that we need to check? We need to check that KW, AW, window factor into the window area is greater than the A wire selected, the selected wire cross section area into the number of turns as calculated in step 4 for from the permeance value. So, if this inequality is satisfied, then you go to the step of actually winding them, and then you have your inductor, which can be inserted into the DC-DC converter circuit. Now, the design of the transformer is also very similar, except a few points. Let me talk about the dissimilarities in the design of the transformer. You see that there is no energy storage in the transformer. We do not want energy storage in the transformer. Hence, the permeability mu, the permeability and hence the permeance are high. It is required to be high. There is no air gap, therefore, the reluctance has to be kept as low as possible. And the design is such that the cores will have very high mu r and little or no air gap. Now, when we look at the transformer, here again we use the two equations V across the winding. Now, let me go to a new page. If you have the transformer winding like this is the primary, N primary, N secondary. This is the voltage across the primary winding, voltage across the secondary winding. Now, voltage across the primary winding equal to N P d phi by dt, which is equal to N P to AC into dB dB by dt. Now, because the operating flux is in the linear region, you can write it as NP AC delta B by delta T. So, in time delta T, which is duty cycle into Ts time, what should be the flux swing? The flux swing goes from minus Bm to plus Bm, 0 to Bm, whatever, depending upon the topology of the circuit and the transformer. So, these two are design parameters which are decided by the designer. This is the core cross section area and this is the number of turns Np. VWP is the voltage applied to the primary which comes from the circuit. So, therefore, you see that the voltage and AC are related through this. And the other relationship, of course, is very similar. AW, KW, AW should be greater than A wire primary, let us say, into NP plus A wire secondary into NS, meaning the same window area should accommodate NP turns of primary via cross section areas and NS turns of secondary via cross section areas. What it would basically mean is that in the window area, if I take a typical core like this, EE core, which you are now familiar with. and if you see the bobbin like this, so on top of the bobbin you wind, let us say, the primary like that. And then you would have a layer of insulation, and then on top of that you have secondary windings, let us say, NS. So, let us say this is NS number of windings of cross section area A wire S. These are NP number of windings of cross section area A wire P, and if there are still further secondaries, you need to isolate them with further layers of insulation and then more windings. So, if there is one primary, multiple secondaries, all of them should fit into the same window area, and therefore, you will have the wire cross section area into NP for the primary, wire cross section area of the secondary wire into NS of one secondary, and so on for all other secondary. So, this relationship has to be this inequality has to be satisfied. Otherwise, all other relationships for calculating the number of turns and then the area product, you see that the other relationship is between this and a wire. The A wire is having IRMS of the current flowing through that winding by J. This is also IRMS, the primary divided by J. This is of the secondary by J, this is of the primary by J, and the current and the AW are linked. And in the earlier equation, the voltage and AC were linked, and therefore, the area product AP, which is equal to AC into AW, is a function of power P, or should say is a function of V into IRMS, or a function of power P naught. So, in that manner you try to do the design of the transformer 2. So, what we shall now do is look at how we go about doing the design of a DC-DC converter in a systematic way, step by step, just like we did the inductor. We shall take the case of two DC-DC converter, generic DC-DC converter example, and see how we go about doing that one, and use the same method to put them into a program like Octave or MATLAB, and then you can iterate the design. So, first let us take the example design of a full bridge forward converter. So, how does the full bridge forward converter look like? So, let us draw that. We have these transistors, and let us have a power supply which provides the DC link, the input, and then across the bridge. So, these switches what I have written could mean BJT, it could also mean IGBT, it could also mean MOSFETs. So, consider them to be any one of the type of the semiconductor switches, and you have the reverse diode connected like this. It is assuming that you have these diodes. If the body diodes are there, you need not put them externally. If they are not there, you have to put them externally. Now, this is the full bridge, and from the center portion of the full bridge, you have a transformer, and the secondary of the transformer is connected in this fashion. Like this. And this is V naught. So, this is one secondary, one primary, and power supply, input power supply. And if you are having multiple secondaries, what will happen is this portion gets repeated as many times as we have discussed a while back while doing control of the multiple output transformers. Now, let us consider this kind of a circuit, and we want to design this DC-DC converter, the power circuit. So, what does it imply? What does it mean? It means that you need to rate the various components. In the case of the power semiconductor switches, you need to select them. You are not making them, you are selecting them from the manufacturer's data sheet. So, what are the information that you would need? You need to know the current stress and the voltage stress and the thermal stresses that are occurring in this circuit topology, and appropriately choose a proper device from the manufacturer's data sheet. You have a capacitance here which blocks any DC going to the transformer, and therefore prevents the transformer flux from walking away towards saturation. This is in fact called the flux walking transformer. And do not forget the dot polarities of the forward converter. This is a buck derived forward converter. And the next, you would of course need to rate these diodes, which need to handle the currents which are flowing through the inductor and the load. You need to design the inductor, you need to design the capacitance, and for each of the outputs. And then of course, you need to design the transformer. So, let us see how we would go about doing the design of such a converter. I have purposely taken a isolated DC-DC converter case rather than taking a more trivial boost converter or a buck converter, because these isolated converters are much more used in practice. We shall after this have a brief look at how you go about designing a flyback converter design, which is actually a isolated converter without transformer. It is not the isolation is by a multi-winding inductor. Okay. So, now coming back to this topic, let us go through the process of designing it step by step. So, step 1. So, step 1, what do? We first have to list down the specifications of the entire converter. Now, while listing down the specifications of the converter, now let us say VDC now let us give simple variables, just VC to represent this. This is VC, so that we do not have very long symbols to deal with. So, now we see the input DC value. You need to give the numbers. If you are taking from the mains, especially the Indian mains, it is 325 volts DC. Now, this is nothing but the nominal DC link voltage. You should also give what is the minimum value that it will take. Let us say some value 200 volts, it swings, and what is the maximum value? It may probably go to 380 or even 400 volts DC, depending upon the power supply input mains voltage swing. And then what is the output V naught? So, V naught is, let us say, 15 volts. Now, if it was just one single winding transformer, we would have put V naught one single scalar value, but if it is a multiple winding transformer, it is better to use vector values, and let us say we need plus 15 volts, and then you also need 5 volts. Okay. Use it as vector. Okay. Likewise, I naught, the output current. So, you may want let us say as 0.5 amps at the 15 volts and 1 amp at the 5 volts output. So, I am just putting some delimiters here, but be careful, whichever it is always better to put all these things into the into a program file like MATLAB or Octave and follow the program's syntax accordingly. This is just for listing down the procedure or process of finding the proper design values. Okay, so that is the design that specification that you would get from the user. In fact, we should call it a specification from the user. You need to also put in some specs as a designer. So, let us say specs designer. The user need not know what these numbers are. He may not even be aware of their meanings, but the designer will have to list down these things. One is delta IL. If you are using an inductor like this buck derived converter, what is the amount of delta IL you would like to give? We mentioned right in the beginning, we discussed it is about we start with a value of 10% of I naught, that is the maximum load current. It could of course vary. You could, if you know the minimum value of the load that would ever occur on the DC-DC converter, that could be also used as as one of the parameters for arriving at the value of delta IL, or if one knows the conduction parameter K, which is 2L by RTS, 2L by R naught into Ts. This is called as the conduction parameter. If this is known, this also could be used to obtain the value of delta IL. If none is known, then the first starting value of 10% of I naught is a good enough ripple current in the inductor, because the inductor ripple current. And then you need to decide the switching frequency. What is the switching frequency? Do you want to switch at 20 kilohertz, 50 kilohertz, or 100 kilohertz? So decide that. I just marked it here as 20 kilohertz, but it could as well be 50 kilohertz, 100 kilohertz, depending upon your application. Then decide the maximum operating flux density for the transformer, and if it is ferrite, fix it at 0.2 Tesla, and maximum operating flux density for the inductor, fix it at around 0.25 Tesla. You can always choose a slightly higher operating flux for the inductance, because the swing in the case of the inductance is smaller than in the case of the transformer. Because if you take the BH curve, which is, let's have this nature, for a transformer, the swing in the flux is from minus Bm to Bm, whereas for the inductor it is in the neighborhood of Bm. It is around this values, because the current ripple is within this band, and therefore you can afford to take slightly higher value of the operating flux density in the case of the inductor than the case of the transformer. Next, you need to have a starting value of efficiencies for the transformers. For low power applications, the efficiency can be as low as 80%. In case you need to rate the input components, like in the input of the primary of the transformer, you take an approximate efficiency of 80%, which will be on the conservative side. And then you need to calculate what is D max. Sorry, not calculate, you need to specify what is D max. Normally, in the case of isolated transformer, isolated DC-DC converters, the upper limit of D is fixed. It should not be more than 50%, because if you go more than 50%, there is not enough time left for resetting the core, and therefore the max limit for D max is 50%, and to be on a safer side, normally 0.45 or 45% is chosen as the D max for transformer isolated cores. And the current density as we have discussed just now, is around 3 into 10 power 6 ampere meter square, kW of around 0.4 if it is transformer, and kW for the inductor 0.6, and the diode drops for purposes of calculation for rating. You can take it as around 0.7 to 1 volt drop per diode, especially if it is higher powers, and mu naught is nothing but 4 pi into 10 to the power of minus 7 Henry per meter. Okay, so these are the values that are needed. Now, with these values, the user spec and the designer spec, you should be able to calculate every component detail. Okay. So, now the calculations. Step 3. Step 3, we shall do the power calculations first. Power calculations. So, P naught is nothing but V naught plus V D, a diode drop, into I naught. Now, this P naught calculation is nothing but actually the secondary power. Secondary power just at the transformer secondary. In fact, we shall name it as PS rather than P naught, so that one should not confuse it with V naught I naught, which is the actual output power. So, PS the secondary power. Now, if you have multiple windings, then it is actually sigma of this. Now, if you want to accommodate for the drops, winding resistance drops, because let us say you have a transformer and the transformer has secondary windings, and there is also the windings of the inductor. If you look at this circuit, you will see that V naught, there will be some drop across the diode. So, that is what we have accounted for. There will be drop across the resistance, winding resistance of the inductor. There will be drop across the winding resistance of the transformer. You can account for them in a conservative way by giving some extra. So, let us say by giving 10% extra voltage more at the secondary. Now, if there are multiple windings, you will have to sum to all secondaries, which would give you the total power reflected on the transformer. Then step 4, what is the turns ratio? So, the turns ratio is nothing but, so let us say 1.1 V naught plus V D divided by 2 times D max Vc minimum minus 0.1 Vc max. How does this come about? So, Vc minimum minus 0.1 Vc max. Now, if you look back into the circuit, you will see this is Vc minimum, this is the worst case, minus around 10% of Vc max, which drops across this capacitance. So, that would be the voltage that occurs at the primary of this transformer. Now, n times will be transferred onto the secondary here, and with all the various drops just discussed. Okay. So, into d max times, because if this is minimum, the max duty cycle would be maximum, would be what the value that you would get here. So, therefore, Vc min minus 0.1 Vc max is nothing but the drop across the flux walking capacitance. This is occurring at the primary, and 1.1 V naught plus Vd is the peak voltage across the secondary. Okay. And this d max is this 2 times d max is basically because of the rectification effect. You have 2 sets of windings center tapped, and the effective duty cycle is actually doubled, and so that is the d max that comes into picture. So, after the turns ratio, let us calculate the duty ratio, d min, nothing but d max into Vc min by Vc max. Now, next step would be to calculate design the transformer. So, let us say transformer. So, in the transformer, first you have the area product, calculate the area product, which is a function of P naught as we observed. So, each transformer will have different equations for the area product. You can work that out by using the Faraday's first law, and the Kw Aw should be greater than A into sigma of A into N. Now, based on that, you would select a particular AP, and therefore, you have AC selected and AW selected. So, once the core has been selected, you can calculate the NP using Faraday's law, which is nothing but Vc max. It has to support maximum voltage divided by 4 Bm AC selected into Fs. This is nothing but from the Faraday's law. Ns is nothing but N times Np. So, if you get fractional terms, you round it to the nearest integer. So, if you have multiple windings, then you can you will see that N is a vector, because we had specified V as a vector. You remember, we specified V as a vector. So, you will actually get N as a vector, and when you use N here, Ns will be a vector, it will have 2 values. So, you can calculate the windings, and after you have calculated the windings, you need to calculate the A wire cross section of the primary, which is, let us say, n I naught by j, and a wire cross section of the secondary, which is nothing but I naught square root of d max by j. So, this all comes from the DC-DC converter analysis itself, and then look into the wires table and you will land up with a wire primary selected and a wire secondary, and that is what you select, and check that kW AW is greater than sigma all of A wires into n, which should be satisfied. Now, after that is done, you would then try to design the inductor. Step 6, I suppose. What was the step number? Step 5, step 6. Step 6, the inductor design. So, inductor design we have gone through today. First, the value of L you calculate, and then after the value of L, area product, which is a function of energy in this case, because it has to store energy. Then the permeance, find out the permeance, then the number of turns, then the wire gauges, that is the wire, and then cross check and see that AW KW is greater than a wire selected into n. So, all these you need to do to design the value of the inductor. Notice that all these equations, the numbers can be obtained from the initial specifications. Then you need to rate the flux working capacitance. Step 7, flux working capacitance, which is the primary capacitance, the one in series with the winding to prevent the saturation, flux working saturation that may happen due to the non-idealities and non-matching power semiconductor devices. So, the flux vacuum capacitor can be designed by allowing some 10% drop across it, and this. Now, remember that this N I naught is the primary current, which is basically the sigma of all. This is the sigma of all secondary reflected currents. Okay. And the voltage rating of the capacitance is also of this order, greater than that. And then you rate the diodes and the transistors. Step 8, we still have the filter capacitor, output filter capacitor at output. So, where you have C, which is delta I L. This is what is flowing through the inductor, and the AC part flows through the capacitor, DC part to the output, divide by delta V C that you need to give into 8 into Fs. Now, the delta IL which flows through the capacitance is this much. This is the ripple that you would want to allow, that needs to be allowed. Now, the output ripple is a combination, it is actually a vectorial combination of not only this plus also the ESR of the capacitance. The capacitance has an ESR which may not be known a priori. Now, both these actually vectorially add up, this delta V as calculated from here and a delta V ESR, both together will contribute to the delta V naught ripple. Now, this portion is normally taken as 10% of the total output ripple, and the remaining is supposed to be across ESR, so that you can have a less stringent ESR requirement of the capacitor. A very low ESR capacitor can be very expensive, and therefore, you try to allow more drop onto the ESR and try to make up by putting a larger value of capacitance, lower value of delta V here. So, just 10% of ripple across C by the fundamentals of the C, physics of the C, delta V variation, and the remaining follows. Therefore, you will be taking 0.1 of the output ripple. Then you could also estimate the ESR of the capacitance should be less than 0.8 times delta V naught by delta IL. And then you have the step 9, the switches, actually the power switch and the diodes. So, let us say you have the diodes first. Now, the secondary diodes will have to have a peak inverse voltage of N times Vc max. Vc max is the maximum that can ever occur across the primary of the full bridge transformer, and N times Vc max is coming across the secondary of each of the center tapped winding, and therefore, 2 times. So, if you are having a center tapped winding like that, this is Vc max, this is N Vc max, this is N Vc max. So, if this is the dot polarity, you have these two adding up, and then one is conducting, the other one is not conducting, and what is appearing across that is 2 N Vc max. You can complete the circuit like that. Okay. So, this should be the peak inverse rating of the diode, it should be greater than this. And what should be the peak value of the current? The peak value of the current through it is whatever I naught, ID max should be greater than, or the IDM value should be greater than I naught plus delta IL by 2 and the average value ID average should be greater than IDM into 0.5 because maximum duty cycle is less than 0.5, or you could say IDM into D max. So, this would be the ratings of the diode. In step 10 is the rating of the switches, that is power semiconductor switches. We see EVO, the collector to emitter, when it is off should be greater than VC max, and the current ICM rating should be all the reflected secondaries sigma of all the n delta IL by 2 reflected secondary peaks plus I magnetizing. And what is I magnetizing? It can be around 10% of I naught to start with. This will be a very small value compared with this value. And anyway, you are going to choose current rating greater than what you have calculated, should account for the magnetizing. So, this way you calculate all the components of the DC-DC converter. Now, let us just do one more, the flyback, and then conclude. The process is exactly the same, only the flyback converter, as you know, is nothing but exactly like the non-isolated buck boost, but you have a winding, another winding across which it is connected. So, how you go about this converter? Sorry for this converter. Now, you see the similarity. If you are using a non-isolated buck boost, you would have done it like this. Now, by putting this extra winding here on this becomes the primary side is still the same. Then instead of hard wiring a junction point here, you have the mutual coupling. In this fashion, and by interchanging the dot polarity like this, rather than having the dot polarity like this, we can do a modification of putting the diode like this and shifting the dot polarity here. So, this will give you this flyback converter So, what you essentially do is you do a design exactly like you would a non-isolated buck boost. So, the process would be start with a buck boost, converter, like this. Now, let us say that we want some V naught at the output, final output of the isolated flyback. 1:n. So, you need V naught here. Then, if the isolation is removed, if it becomes 1:1, it would be V naught by n. Keeping V naught by n as the voltage output of the non-isolated buck and I naught as actually I naught into n as the current which flows through it, such that we keep the power same as the isolated case. Do all the design that you would for the non-isolated buck, find out the value of the inductor, the rating of the switch when the switch is on, the current that flows through this peak current would be the inductor current plus delta IL by 2, and when it is off, this is connected, the voltage across that will be voltage V in plus V naught by n. So, the rating would be across this voltage rating VCEO would be V n plus V naught by n, same as here. And the inductor value can be calculated, and once the inductor value is calculated, find the energy to area product, follow it up with permeance, then the number of turns and the wire gauge. So, once you have decided that, there is a small modification you need to do at the inductor, and that is the K factor. So, when you design this inductance, now do not take the K factor of Kw of 0.6, take Kw of 0.4. If it is still many more windings of even 0.3. That is one change that you would do, and then when you do the cross check, Kw should be greater than not just only the primary winding, a wire of the primary into Np plus a wire of the secondary into Ns. This is Np. If this is Ns, that would come into the picture there. So, once that is done and the connections are made according to this, you will get exactly the output that you would have decided, because the 1:1n ratio will come and figure in automatically, and you will get V naught here and I naught. Rate these diodes according to the secondary current flowing, that is the I naught currents and the capacitance currents that flows through here. That is, I capacitance current and the I naught. So, accordingly rate the diode here without the n factor. Now, this way you can make a quick design of the flyback converter. Flyback is very popular, and even though the quality of the output is not as good as a forward converter because there is no output filter inductor, the flyback converter is very popular basically because of its very low component count. You see that there is only this diode, the capacitance, one inductor cum transformer, isolator, and the switch, power switch. So, this gives a very cost effective design, even though one need to sacrifice to some extent on the quality of the output voltage. So, with this let us conclude the topic on this DC-DC converter, and I hope that you will be able to design a complete DC-DC converter, analyze it, make the design the values of the power circuit, design the controller, and then implement it together in a simulation package like ngSpice, and then subsequently bring it to an electronic breadboard and implement it in hardware. So, these sequence I hope you will be able to follow and analyze them fruitfully. Thank you very much.